Good morning, everyone. I am Vinita, working as an associate professor in the Department of Electrical and Electronics Engineering, RMD Engineering College. Today, I am going to explain a topic in stability analysis in power system analysis. And here, today, we are going to discuss about the calculation of critical clearing angle and critical clearing time for a double circuit line. Here, is a generator which is connected to an infinite bus bar through a double circuit line. Here the input to the generator is PM, mechanical power, and it will be given to the, that is, it will be connected to the infinite bus with a voltage of V angle 0 degrees. And here the circuit model for the same system that is given here. And here this is the equivalent circuit of the generator and its reactance XD dash. And the voltage for the generator is modulus of E dash angle del. And for the transmission line, it will be represented by its reactance X1 and X2, which is connected to the infinite bus. Here, we are going to analyze the system under three conditions. That is steady state condition, means that is before the occurrence of fault, during the fault condition, and then after the occurrence of fault. It will be termed as pre-fault condition, fault condition, and post-fault condition. All these three conditions, we are going to see the changes in the system. Here, under steady state conditions, so steady state condition means before the occurrence of fault. That is called as pre-fault condition. So during pre-fault condition, whatever the input is given to the system, that will be delivered at the output. For example, if the input power is mechanical power, we will be receiving the corresponding electrical power at the output side. And so here, the electrical power output during this steady state condition is given by PE1 is equal to E dash into V, that is modulus of E dash into modulus of V divided by what is the total reactance here? That is for generator, it is XD dash plus here these two reactances X1 and X2 are connected in parallel. So X1 parallel X2 into sin del. This can be written as P1 max into sin del. So this is first case. And similarly, if you consider when the fault occurs away from the line ends, that is here we can assume that the fault has been occurred at the middle of the transmission line. So if the fault occurs at the middle of the transmission line, what is the change in the output power that we are going to calculate? So if the fault occurs in the middle of the transmission line, its reactance, that is the circuits, the line gets divided into two, and so its reactance can be calculated as X2 by 2 and X2 by 2. It is equally divided. So the reactances are X2 by 2 and X2 by 2. And this can be, the circuit model can be reduced using star delta conversion method. Here, the three conditions are given here. So first one is we can assume pre-fault condition. So what is the output power of the pre-fault condition? P1 is equal to modulus of E dash into modulus of V into sin del divided by X D dash plus X1 plus X2 divided by X1 plus X2. That is just now in the previous slide I have explained. Two reactances X1 and X2 are connected in parallel. If two reactances are connected in parallel, the equivalent reactance is X1, X2 divided by X1 plus X2. So finally, it can be written as P1 max or P max 1 into sin del 1. This is for pre-fault condition. Similarly, coming to the post-fault condition. So what is meant by post-fault condition? It is nothing but after the occurrence of fault. So after the occurrence of fault, what will happen? Here we have assumed that the fault has been occurred at the second line. So second line at the, that is middle of the second line. So if the fault occurs means immediately the line has to open to clear the fault. Okay. So if it is open, then we'll have only one line. That is this first line we will be getting, and the second line is open during this faulty condition. So here we can see the diagram here. During this post-fault condition, the diagram becomes for generator and its reactants. And in the transmission line, we will be having only the first reactants X1. Therefore, this output power during this post-fault condition can be written as PE3. So for the pre-fault condition, it will be represented by PE1. And for post-fault condition, the output power is represented by PE3. So again, we have to apply the same formula. It is nothing but E into V divided by X into sin del. This is the general formula for PE, that is the output power or the electrical power. Since here, the input side, we have the voltage of E dash, and at the output side, that is for the infinite bus, we have the voltage of B. This can be written as modulus of E dash, modulus of V divided by XD dash plus X1. Now, only one reactance we have, it is X1. Therefore, XD dash plus X1 into sin del. This can be written as this, that is E dash into V divided by XD dash plus X1 can be written as P max 3 into sin del. This is second case. Now, third case, during the faulty condition, we have to write the model for this. We have to draw the model and we have to derive the expression. So, during this faulty condition, the circuit diagram that will be like this. Here the fault has been occurred, and so that its equivalent circuit becomes like this. So this is your equivalent circuit. So if you see the circuit, you can able to identify the reactances. So the input side, the reactance is XD dash. And here we have the reactance X1. And this becomes, it is just like delta connection, or we can call as a pi connection. This is X1, and these two will have a common potential. If this fault has been occurred, means this will be connected to the common ground point. So this circuit diagram, which will be, it is just like a delta connection. So if you draw this equivalent circuit, you will be getting the delta connection like this. This is X1, this is X2 by 2, and this is X2 by 2. From this, we need to write its equivalent reactance value. So for if it is in delta connection, we have to convert this delta into star. So you have to apply the formula to calculate the value of XA, equivalent XA and XB. So to find the value of XA and XB, all of you know the star delta conversion. So if you want to convert this XA, you have to take these two adjacent values, adjacent reactants like S1 and X2, that is X1 into X2 by 2 divided by all the three reactances X1 plus X2 by 2 plus X2 by 2. So therefore, what will happen? In the numerator, we will be getting X1 into X2 divided by 2. In the denominator, we will be getting X1 plus X2 by 2 plus X2 by 2. So what is X2 by 2 plus X2 by 2? It is nothing but half plus half becomes 1. So X2 by 2 plus X2 by 2 becomes X2. So in the denominator, you will be getting X1 plus X2. In the numerator, we'll have X1 into X2 divided by 2. So the value of X2 that comes in the denominator. Similarly, by applying the same formula, you have to calculate the value of XA. That is, you have to apply star delta conversion like XA and XB. So after calculating the value of XA, XB, XC, if we draw the equivalent circuit, we will be getting the corresponding star connection. So already we have XD dash. In addition to this XD dash, this X1, X2 by 2, this X2 by 2, this becomes XA, XB, XC. This is the equivalent of this delta connection. Now, again, we need to convert this equivalent star into delta. For this also, you have to convert the formula for delta to star conversion. So, if you convert this star delta conversion, again, this is the formula to calculate this star delta conversion. So that this is your equivalent reactance value, X11 is equal to xd dash plus xa into xc plus xc xb plus xd dash plus xa into xb divided by xc. So this is the final equivalent circuit after converting this star into delta. So this is the star connection. Now from this we can write the output power for the second case, that is during the faulty condition. So what is the output for power? In the input side the voltage is E dash, output side the voltage is modulus of V divided by the reactance is X11 into sine del. So this can be written as P max 2 into sine delta. So during all the three conditions, that is pre-fault condition, post-fault condition, and during fault condition, we have calculated this output power PE2. And for this, we can draw the power angle curve. So here the power angle curve which is drawn between PE and del. So how to draw the power angle curve? So we have to take the values between PE with respect to del. So first we have to draw the characteristics for pre-fault condition. So here if you see the first characteristics, that is for pre-fault condition PE1. So initially the system that is in steady state condition. So during steady state condition, PM is equal to PE. So this A represents steady state condition. Okay. Then after this pre-fault condition, we have to assume that the fault has been occurred. So if the fault has been occurred, what will happen? Immediately at the output side, the current becomes zero. So if the current is zero, the value of PE that is also zero, because P is nothing but the product of voltage into current. So the value of I that is also zero. So since the value of PE is equal to zero, it will be starting, that is the value of PM is equal to PE from this point A, that will be started to decreases towards this point B. So here the value of power will not become to zero, because since we have another one line, the power will be transferred to that line. So what will happen means the output power will be reduced and it will not be equal to zero. So here now the operating point that becomes B, and during steady state condition, the value of rotor angle is nothing but del naught. Now this is for pre-fault condition. Now, so after the fault condition, what will happen? The circuit breaker contacts will be open to clear the fault. After opening, what will happen? Immediately, if the fault has been cleared, the circuit breaker has to restore its original condition. That is, the contacts will be closed and the circuit will be regain its normal condition. So again, the current will be flowing through the circuit. So the operating point now will shift from B point to C point. So at B point, what will happen? At A point, the fault has been occurred. So the circuit breaker contacts has to open. So if the circuit breaker contacts is open, the current value that become reduces, and so PE also decreases. The operating point comes to point B. Now again the circuit breaker contacts get closed. Current will be flowing from the input side towards the output side, and so the operating point and the output power started to increases. So the operating point that shifts from B point to C point. Now here the corresponding angle is del C. Del C is nothing but the clearing angle. That is, the fault has been cleared at this point. So during this point, the corresponding rotor angle has mentioned as del C, and the corresponding time period to clear the fault will be represented by TC. That is called as critical clearing time period. Now what will happen? Since the fault has been cleared, immediately the power value that will be increased from the C point to D point, and finally the operating point that will be shifts to E point. That is, if the fault has not cleared at this del C, then what will happen? This del value, the rotor angle, it will not be there in the same position, because continuously we will be giving the input. So the rotor angle that will be oscillating with respect to its equilibrium condition. So what will happen? It will be continuously operating. That is, the rotor will be continuously oscillates. So the operating point will shift from point D to point E. Now here the operating point that becomes point E and the corresponding angle is del 2. So this point that is called as, this is the operating point corresponding to post-fault condition. So post-fault condition means after the clearance of fault, the system will settle down to the a point that is called as E, and that point that is called as the operating point during the post-fault condition. And if the fault is not cleared at this point E, again what will happen? This rotor angle has to be moved from this del 2 towards the maximum point. So again, this del value will not be at will not be in stable. It will be continuously oscillating. So again, this delta 2 that will be shifting from delta 2 to delta CC. That is called as critical clearing angle. Here you can see initial angle del naught, and this is del CC, and this is del max. This already I have explained in equal area criterion, and during this condition also the concept remains same. During initial condition the angle is del naught, next it becomes del C, clearing angle. If the fault is not cleared at del C, again the rotor angle that will be oscillates, and that will be moves from del CC to del max. Now here we have to check whether the areas are equal to check the stability condition. If these two areas A1 and A2 are equal, then we can say that we can achieve the condition for equal area. That is, if A1 equal to A2, we can obtain the stability condition. Otherwise, the system will become an unstable condition. So here we can say the area that is equal to A1 is equal to A2. So for this areas, we have to apply the formula to calculate the corresponding del CC and TCC we can calculate. So if you calculate the value of angle del CC, we have to apply the condition A1 is equal to A2. So what is A1 and what is A2? A1 is the accelerating area and A2 is the decelerating area. So generally the formula for accelerating area is PA into D del with respect to the corresponding period, that is equal to 0. Now here the area for accelerating area is PA into D del, and what is the period for this? What is the angle for this A1, area A1, del naught to del C. Similarly for A2, the angle is del CC to del max. Minimum is del CC and the maximum angle is del max. This limits we have to apply here to calculate the value of del CC. So what is PA into D del? It is nothing but acceleration area. So acceleration area means which power will be maximum? PM is greater than PE. PM minus PE into D del. So this can be written as PM minus PE into D del. Here we need to apply the condition PM into, if you apply the limit for del, we will be getting del CC minus del naught minus PE2 into D del. So PE2 we have the formula. That's why here we have not applied the limits. And the limit is del naught to del CC. That is equal to a decelerating area. So in decelerating area, which power will be the maximum power? The output power PE that will be higher than the value of PM, mechanical power input. So the formula becomes PE minus PM into D del. So here PE becomes PE3 into D del minus PM into, you can apply the condition del max into del CC. Now, so again, you have to apply the value for PE2. This first term is PM into del CC minus del naught minus integration of del naught to del CC. What is PE? PE becomes P2 max into sine del into D delta. And similarly, third, that is the right hand side, we'll have the decelerating area. So decelerating area formulas P3 max into sine del minus PM into del max minus del CC. Here we will be considering the third one, that is A2 area. If you take this A2 area, the limit is del Cc minus del max, and here the value for PE is nothing but PE3, that is post-fault condition. That's why here we are substituting the values. Here we are substituting the values P3 max into sin del. P is equal to P3 max into sin del. Already we have derived. So now you have to multiply all the values and you have to apply the limits. And if you simplify all the, that is, if you simplify step by step, and finally we can calculate the value for critical clearing angle del Cc. So del Cc is equal to cos inverse of Pm into del max minus del naught plus P3 max into cos del max minus P2 max into cos del naught divided by P3 max minus P2 max. So this is the value of critical clearing angle for the condition of the fault occurs at the middle of the double circuit line. Thank you.